Hi, my name is Rozner. This is Synfuzz, Building Language-Aware Fuzzers. This is a highly condensed version of the abstract that was in the program. There were some scheduling conflicts that necessitated turning this into a stable talk. Oh, is that better? Apparently. All right. Let's see if that will stay. So I tried to keep in all the relevant information. If there's something you're lost on, just yell and I will explain. So to get started, if you've ever tried testing software with really highly structured input data, you've likely run into a handful of problems. And ultimately, this comes down to the fact that testing structured input is really hard. And examples of this are things like compilers, interpreters, complex network protocols, things that have really structured data where there is maybe information that is in one part that's going to be used somewhere else to determine how to continue to unpack or understand something. Terminal menus if you're in interactive programs. Places where you really need to make sure that you're testing like the right series of things that get you to a place in the application that will have some kind of interaction. And it's hard for a handful of reasons. The first being that simply getting your test cases is a really hard thing to do. If you've ever worked on software, you know that test cases are not always super common, and depending on how strict your team is, you may or may not have good test coverage. If you're in open source, you kind of have the benefit of getting access to the actual test cases if they exist. If you're working on, say, reverse engineering something, or you are trying to determine whether or not something you're building is going to be compliant with something else out there, you might not have the closed source test cases. It just is part of the actual product's source code, and you don't have access to that, so you're kind of limited in what you can get access to. Understanding code coverage is sometimes difficult. There's a lot of tooling out there that will inspect the application, will trace execution through there, and kind of show you where you have explored in the application. But that's not always available, and just because you've been to a place doesn't mean you've really exercised it. State is a thing. It's very rare that you see truly stateless code, and so just because you got to an area with some certain state does not mean that different state will not have some completely different behavior. High code coverage does not always equal well exercised. And so like if you're trying to test a parser or something that uses a parser to validate an input, if you don't get past that initial parse, you might not ever get to anything interesting in the application because it's that gatekeeper and it's stopping you from getting to a place where that information is being used. So you want to avoid uninteresting input, stuff that's not going to get you past that point. And so typically a lot of off-the-shelf fuzzers and tooling out there is going to look for very specific conditions. Looking for cases of, did I crash the application? Did it end in a seg fault? Did it end in a sig abort? What's the return value of the application and what did it do? So you have limited flexibility in determining, your failure cases and understanding, did that do something interesting and do I want to continue down this path? You also have pretty limited flexibility typically in creating that feedback loop in terms of how you want to modify your input for that next iteration as you generate your next input. So that next mutation you're going to perform to the input to see, am I doing something interesting now? A lot of the time, as we'll see, they're just based on randomness and a handful of other techniques. But ultimately, for any sufficiently large or complex program, you're probably going to want to use some sort of automated test generation. Fuzzing is just one of those ways you're going to become effective in trying to get good coverage and understand that you feel comfortable with how much you've tested this. It's the only way you're going to get billions of test cases out in any reasonable amount of time with a reasonable amount of work. There's a lot of different ways you can do this, and a lot of different techniques. We're going to focus on grammar-based fuzzing, and essentially what this does is it takes a grammar file, and when I say grammar file, when you're building a language, you typically will define a grammar, whether it's context-free or regular or context-sensitive or Turing-complete, but you're going to define this grammar. And if you're using a parser generator, you're going to feed this grammar in, and it's going to spit you out some code that will recognize that language. So we're going to take this grammar, and from that grammar, we're going to do the opposite. Rather than trying to parse input, we're going to generate input from that grammar so that we know that it's syntactically correct, and we don't have to worry about that case of sending an input that's not getting us past that initial parse phase, at least hopefully. As I've said, if you're using these tools, they all have their own grammar definition languages. So whether you're using like Bison or Yak or Antler or any number of these different tools out there, they're all going to be subtly different. Their parsing algorithms are different. The actual definition language is different. And because of that, you typically, for the tools out there, need to end up rewriting a lot of these grammars in the very specific language that the tool expects. So examples of tools that do this are Mozilla Dharma, which is an open source project that they use for testing browsers, so for HTML, CSS, JavaScript. There's also a really great paper called Fuzzing with Code Fragments that introduced a tool called Langfuzz, also out of Mozilla. This is not open source, and as far as I know, it's not available generally. Both are really good places to start looking at for more information about how this works. But the idea is they both take these specific grammar languages where you define your grammar, and you have to translate the grammar that you're working with to this language. And that's not necessarily an easy thing to do. You're talking about grammars that might be tens of thousands of lines long, super complex, and maybe the syntax or the semantics of it are subtly different from how a different one might work. And so you need to be really careful when you do this that you don't change the semantic meaning of what that grammar is showing. And that's really hard. They're also typically limited to context-free grammars or regular, specifically with text-based input. And this is great if that's what you're looking to test. But if you're trying to do, binary file formats or network protocols that are all binary based, you're typically pretty limited in what you can do with these tools because they just don't give you the freedom to express that language. So what can we do to do better? As I said earlier, one of the things that is a big problem is the ability to build custom test harnesses. Most fuzzers and tools out there that are in this vein, like I said, they look for very specific things. Did I crash the application? What's the return type? What signal did it throw at the end? And so being able to have more flexibility in terms of determining, am I seeing something interesting? And determining, is there something interesting I can get out of this? Is there some information that's sharing? Is it leaking that I can determine something more from? Being able to directly use the grammar from our parser is great. If I've already gone through the process of writing a parser, so in the instance of one of the reasons I built this is we built our own implementations of a handful of different SQL parsers because we needed it for an analysis tool. And one of the big problems we're trying to figure out is how close is our grammar to the original one? What do we parse and how does it affect, how similar is it to the real one? And if we were going to have to go and take this 15,000 line grammar definition and convert it over to the grammar definition that, say, Dharma uses, we're not going to be able to manage that. As we make changes in one, we're not going to be able to go and update it and keep them in sync, and we'll never be able to really know that we're doing the right thing here. Expressivity is another one, as I said. Having the ability to do these common things like text-based, context-free, and regular, but having more than that. Being able to really hit the binary stuff. If we want to do like complex file formats, like ELF files or PE files where there are fixed offsets in there that need to be correct so they can go to the right place and get information. So being able to have that breadth and do more with it is something really important. Being able to use it from other languages, this is another thing. There's a lot of tooling, especially for parser combinators, where it's built for a specific language. Like for instance, Antler was built for Java, and there's a lot of really good tooling for it in Java. But as soon as you deviate from that platform, getting access to that tooling is pretty difficult. What if you could use this in Java, but also use it in Ruby or Python and Go? So having that flexibility to use this code base from anywhere would be really helpful. And as I said, reusing as much as possible. Let's avoid duplication, because when we start talking about inputs this large, there's no way we can keep track of this. We need to make sure that we're using like the original source material, and we're not going to get into the place where we have to manage multiple ones. So as I said, this has been released since around DEF CON. The architecture ends up looking something like this. At the base, you have Synfuzz, which is, it functions mostly as an intermediate representation. So you build front ends that will recognize individual grammar languages. So you could have one for Antler, one for Regal, one for eBNF, Bison. And what these do is it reads in a grammar file for their specified format, and then will translate that to the Synfuzz syntax tree. And then from there, you can generate test cases and use that to build your own test runners. And so by making this code-based and making it so that you don't have to, it's very much not out of the box like you would get from something like, say, AFL, where it will just run on a binary and fill in stuff for you. But it allows you flexibility in that you can build a lot of your own tooling and look for very specific things. And we'll look at how we're going to do that in a few minutes. But the important thing to note is that we can build tools like that from this. And the idea with this is that you should only ever have to write your own test harnesses. You shouldn't have to write your own front ends. Those will be built for you. Right now, Antler exists, and I'm planning on building out more. So let's take a look at how this works and how you might do it. At the most basic level, you get the combinator interface that Synfuzz provides you. And this is how you express a grammar, and any front end will end up converting. So this is writing in the pure combinator language within Rust. And if you've ever worked with the combinator library, it will look probably pretty familiar to you. At the top here, we're declaring a generator for a number, which is essentially just a sequence of the numbers 1 to 9, and then a sequence followed by 0 or more of 0 to 9. And so what this is doing is building up an expression. So something like number plus number, or number times number, as complex as you want to go from there. So we have our operators, we have our numbers, and then we have the expression that combines all that together. To use this, we can go a little bit deeper, and we can use one of the front ends. This is the Antler one. And so this is essentially all that's really required, is you provide it a grammar file, you read it in, you generate the rules from it, which is basically just parsing it and then translating it into the intermediate representation. And then you can pick a starting point. So in my case right here, I'm using the node root, so that's like the top of the tree. But if you wanted to say generate just some subsection of that grammar, you can say, I want you to start here, and it will build you a tree down from there and just generate subsections of that language. Below that, it just kind of gets you the string out of there, and it will print it out. This is like the most basic example. You can pretty much use any method you want for pushing this into a program. The full socket API, if you want to send it over the network, you're good. You get pipes, files, anything you can use at the operating system level, you have the flexibility to use with this. Let me see if I can see the right one. So as you can see here, this is the executable showing the very first example that I showed. This is the expression, and you can see me running it multiple times here, and it's is it the projector?
No, it's really, really small. The projector only can go with the solution, but hard to blow it up and that's invisible.
Cool, okay. So as you can see here, it's running through, and every single iteration it takes, it will generate you a new string. 100% random, it's coming from that grammar we fed it, and it will give you a new one every single time, so long as the randomness doesn't generate the same values. So we've seen how we can use this now. Let's talk about designing test harnesses, because that's really where we're probably going to spend a lot of the time using a tool like this. At the most basic level, this is like what we typically see most fuzzers doing is, did it crash? Did it do something that is like considered bad? So to do this, we can, use something like popen or exec. We start the process. We generate some input using the code snippet that I showed earlier, and we feed it into the application using whatever mechanism, whether it's a socket or a pipe or standard in or argument or environment variable. And then we listen for it to end. Does it halt? Does it halt with a signal that we understand? Is it a seg fault? Is it seg abort? Did it do something interesting we can do? And this is essentially the state of where we are with most common fuzzers today. We can replicate that functionality by doing something just like this. Once this happens, we analyze the crash. We see if it did something interesting. Do we have access to modify the instruction pointer? Can we take control of this? The answer is yes. Cool, we found something interesting. Let's go a little bit more esoteric, a little bit more interesting, something that we can do that you can't typically do with one of the off-the-shelf fuzzers today. As I said before, one of the main reasons for building this was to test reimplementations of parsers that we didn't know if we were going to be replicating the correct behavior. How do we determine if our implementation is overfit? The case that we are parsing things that the reference implementation doesn't. So one of the ways you can do that is you set up your test harness same way. You generate a test case, and you need to find an oracle. And what I mean by oracle is it's some mechanism for determining whether the error that you're getting back is either a syntax error or a runtime error. If it's a syntax error, then it means that the grammar that you fed it and generated input from is going to be not the same as the one you're testing against. You have generated something that your grammar says is valid, but the reference one does not. If it's a runtime error, there could be some state involved where you generated something that passes the parsing phase, but there's something about the internal state of what's going on that is not semantically correct. So once you find an oracle that will provide that information to you, you can use that to make those decisions. So one example of this is something like in MySQL. There's two examples here of errors you might get from sending a SQL query to MySQL. The top one here is a syntax error, where it specifically says there's an error in your syntax, and it shows you kind of where it happened. And this is a case where we wrote something that never passed the parsing phase. If you go below it, you'll see a runtime error. The table MySQL A does not exist. And this means it finished parsing, it validated the sentence. The sentence is a correct sentence in that language, but something in the state, the database, the schema, it's not meaningful. There's something wrong with the statement, but we know we got past that. So we're getting to the interesting points of the application, which means that we're not overfit. Cool. The converse, you have underfit. Does the reference implementation generate sentences that are something that our parser does not match? If we have access to the actual grammar, we can do the opposite, where we generate from the reference implementation. So in the case of open source software, if you get access to that, You can generate from there and feed it into yours. If yours comes back and says this isn't valid, then it's something that's underfit. So quick other demo. I don't know that I can get this visible. So this is an example testing actual MySQL. So I used the public available MySQL grammar for Antler and built a test harness around that same methodology where it will basically generate and then send to there and then identify the error message coming back and determine if it is a syntax error or some type of runtime error. So here I'm feeding it in a starting path of create table. So it's going to generate me a whole bunch of statements that are create table statements. And you can see here on the left, there's no tables there. I'm going to hit play and it's going to go through the process. So it's running there on the right, and it's just iterating through those create statements. You'll see it spitting out syntax errors. Those are all strings it generated that it passed to the MySQL database, and the database said this is a syntax error. So there are clearly issues with the grammar that were being used. You also see on the left-hand side, it goes from having 0 tables to like 1,000. So it's pretty quick in generating these values. What would I just do? So what's ready today? You have access to Synfuzz. This is a public open source project that I'm still working on. There's a ton of stuff happening on it in terms of getting more front ends built out for it, as well as adding more functionality to it. Some of the things I'm working on right now is cycle detection and forcing progression. So you can get into places where there are significant amounts of recursion that can cause stack overflows. So fixing that problem and making it possible to use very recursive grammars. Exposing C bindings and other language bindings so you can actually bring this into any language you'd want to. Negation logic is complicated. Context sensitive and introspective grammars and functionality to handle that. And then grammar coverage information. So understanding how much of the grammar we've explored and what we've generated from there, and the ability to tune that. Cool. That's it. Thank you.